Yeah, so good evening, all, and welcome you all for the fifth lecture in Electronic Circuits 1. To summarize lecture number 4 and what we discussed in last class yesterday, anyone?
Sir, we saw
Last time what
selection
we
of
discussed?
Q points, sir.
So first I started with very good selection of Q point. So
Sir,
where
are
you
you
will select your
presenting,
Q
sir?
point? Oh, not sorry. Wait, no, wait. Is it okay?
Yes, sir.
Yeah, sorry for that. I thought I said it. Huh? So sorry. So coming to review of lecture number 4, okay, as he told, so I started with the selection of Q point, okay, so selection of Q point. So where you want to choose your Q point, okay, if
Center
you
of
will
DC
choose,
load line, sir. Active
okay, before that, if it is nearest to, if it is, sorry,
saturation.
yeah, wait, nearest to saturation region, what will happen if it is nearest to cutoff region? Then what will happen? Yeah. Now tell me, ma, if it is nearest to saturation, then what will happen?
The positive part will be clipped off, sir.
Okay, if it is nearest to saturation, so some positive portions, okay, will be clipped off. Similarly, if it is nearest to cutoff, then some of the negative portions, okay, will be clipped off. So in both cases, actually, you will get what type of signal? Will you get distorted or undistorted?
Distorted, sir.
So you will get a distorted signal. So will you get stable or unstable signal? So you will get
Unstable,
unstable
sir.
signal. Okay. So now coming to case number 3. So where you want to choose, okay, your DC load line, where you want to choose your Q point at DC load line, okay, at the center, right? At the center. Now if you will choose, okay, at the center of the DC load line as well as at the center of the active region, then what will happen? You will get undistorted output, right? So you will get undistorted output. Yeah. So you will get stable output. Right. So let me draw that once again. So take case 3. I want to draw it once again. Okay, now this is my DC load line. X-axis VC in terms of volt and Y-axis IC in terms of milliamps. Okay. So now take this is my DC load line. Take this point is A, that you know the value, and this point is B. So where you will choose your Q point at the center, right? Okay, now it will act as, yeah, it will act as the reference point for your signal. Okay, now take, suppose this is my 10, 0. This is assume some 0, 2 milliamps. Okay, so where you will fix your Q point at the center, right? So Q point must be, what's the value for this Q point? What is the center for 10? 5. What is the center for 2? So 5, 1. So this is my 5 volt and this is my 1 milliamps. Okay. So here you will fix your Q point. Then what you will do, you will give some input. Okay, take this is my signal 1. Okay, and you will project this. You know what could be the corresponding output for this. Okay, yeah, you will get undistorted output. Now pick some other color. This time I want to give a large signal when compared to the previous one. Okay, so now what is my output for this? Okay, now yesterday we have seen this, right? Now my question: what is the need for catching DC load line? It's very important. Yesterday I forgot. Okay, to tell this. What is the need for catching or drawing DC load line? Why? And why is it so called DC load line? That I will explain now. DC load line and what's the need for sketching it? Okay. Any idea? What's the need for sketching it? Now, what is the maximum output voltage? What is the maximum output seen? Any guess from this red color signal? The large signal, what is the value? What is the amplitude for the large signal? What I have taken? I have taken A equal to 10, 0. So 10 volt. So what is the maximum output voltage? The maximum output voltage is given by this range, right? This range, right? This is my maximum range. Okay, here this is my maximum range. So what is the maximum output voltage? What is the amplitude of this sine wave? Maximum. How much? Anyone? Are you with me?
2, sir.
10, sir.
10 volt, right? Yes, first I want to speak in terms of voltage. So it's 10 volt. What's the 10? What's the value for this 10? Actually, this is my VCC, right? What is the value for this 10? This is my VCC, right? So actually, this is my biasing voltage. So what's the conclusion? And what's your observation here? DC load line, it is used to predict the output, right? You may design some circuit, you will give some input. What is the maximum output for that circuit? That is predicted by this DC load line. See the beauty. You design some circuit, right? And the circuit la, what could be the maximum output voltage? Maximum 10. Suppose if you will give 15 volt, what will happen? Will you get undistorted output? Suppose if you will give 15 volt for the same DC load line. So by seeing the DC load line itself, it is easy to predict the maximum output voltage, right? So the answer, what is the need for sketching DC load line? To predict, okay, the maximum output voltage. To predict the V max, maximum output voltage, the V max at output. Okay, to predict the maximum output voltage. See the beauty. Have I given any input? Have I given any input? Anyone, please answer.
No, sir.
No, but DC load line, it is giving the maximum output voltage. That is the beauty of, that is the essence of DC load line. By seeing the circuit diagram itself, it is easy to predict the maximum output voltage, okay, without giving the input voltage. ஒரு இன்புட் வோல்டேஜ் கொடுக்கறதுக்கு முன்னாடியே ஒரு சர்க்கியூட்டை பார்த்து ஈஸியா அந்த பயாசிங் வோல்டேஜ் என்னவோ அந்த பயாசிங் வோல்டேஜ் தான் மேக்ஸிமம் வோல்டேஜ். ஓகே, அதுக்கு மேல நீ கொடுத்தீங்கன்னா என்னதான் கிடைக்கும்? யூ வில் கெட் distorted output. You won't get undistorted output, right? So now got the point. What's the need for sketching DC load line? What's the need for sketching it? Anyone? What's the need for sketching DC load line?
It gives the maximum output voltage range.
Yeah, without, but the beauty is without giving any input. That's the beauty. Okay, now got the idea, right? What's the need for sketching DC load line, right? To understand in a better way, now take this problem just to understand. Okay, Now take this problem. Assume this is an amplifier, right? I don't want to sketch the amplifier. Just to put it in a black. Assume this is an amplifier, and assume the biasing voltage of 10 volt. Okay. And the gain, voltage gain, assume some 5. And I am giving the signal like this. Okay, peak to peak 1 volt, minus 1 to 1. So peak to peak 2 volt. Okay, and assume the voltage gain is 2. Yeah, 4. Yeah, voltage gain is 4. So here the input voltage is actually 2 volt. So peak to peak 1 volt. So what's the output voltage for this amplifier? Anyone? Now take this problem. Find V out. Simply write. No need to sketch the waveform and all. Tell the magnitude alone. What is the output voltage in terms of numbers?
8 volts.
Anyone? My input. So Vi, just simply take 2 volt and voltage gain 4. So obviously you will get V out, which is equal to AV times Vi, that you know it, right? Since you know what is voltage gain, right? Output voltage divided by input voltage. So from this, what is output voltage? AV times Vi. So where AV I have given 4 and the input I took, so 8. So you are expecting 8 volt, so you will get 8 volt, nothing wrong. Okay. Now take problem number 2. Take the same problem. This time instead of this is for case A. In case B, this time instead of 2 volt, I want to give 3 volt. Now what is the output voltage? For case A, the output voltage is V out equal to 8 volt. That you know. Okay. Now for case B, what is the output voltage? Anyone? Same voltage gain 4. This time input is 3. So what is the output voltage?
12.
12 volt.
12. யார் இந்த அறிவாளி? வா. இதுதான் நடத்திட்டு இருக்கேன். DC லெவல் என்ன சொல்லுது? What would be the maximum output voltage? What is the maximum output voltage? Yeah, very good. Actually, as per calculation, you are expecting 12 volt, but you won't get 12 volt. Why? Because the biasing voltage is only 10. Then how can you expect 12 volt? Got my point? Everyone, at least put S in chat box.
Yes, sir. Yes, sir.
Yeah. Only 3, 4, 5. Yeah, thank you. So, got it? So, the maximum output voltage, nothing but the biasing voltage. That is the key point. Okay, thank you. So, V max, which is nothing but biasing voltage. Just to understand. Okay, so here you told now if we will give 15 volt, okay, in this DC load line, okay, will you expect 15 volt? No, because the biasing voltage is 10 volt, I assumed. Then how can I expect a 15? It's not possible. So from this DC load, it's easy to predict the output, maximum output voltage. So according to this DC load line, the maximum is 10. So the maximum output voltage is only 10, not 12. Okay. So you are expecting 12, but what is the output voltage? V out equal to 10 volt. So if you will give 3 volt, you will get 10 volt. You want to know why? Okay. So this is the maximum extreme. Okay. So now this is the need for sketching DC load line. Okay. After DC load line, what I started? After DC load line. Anyone? So started with the DC biasing, right? Okay. So what is biasing? Started with actually biasing. In biasing, we are having 2 types. Yeah. What is biasing? Simply called giving of.
Giving external circuits.
So giving of external circuit. External voltages. Okay. The
Voltage,
voltage
sir.
may be DC or the voltage may be AC. What's the need for DC biasing? What's the need for DC biasing? What's the need
To
for AC
trigger or
biasing?
activate the circuit, sir.
So to trigger, okay. What's the need for AC?
To produce stable Q point.
Yeah, to produce the stable Q point. That we will discuss after some time, how it is producing stable Q point, okay. So now, and after that, we started with the DC biasing, right? Yeah. In order to work transistor as an amplifier, it must be biased in active region, right? Okay, so how will you bias the transistor? Now, input junction forward biased, output junction reversed biased. That story you know. And after that, we started with what are all the factors, okay, affecting the stability of Q point, right? So put the heading factors affecting stability of Q point. Okay. Actually, what we are doing, we are giving constant voltage, okay, to the junction of the transistor. So when, yeah, we are giving constant voltage, right? So when you are increasing the biasing voltage, when biasing voltage increases, actually what will happen? Temperature increases, right? Upwards increases, downwards decreases. So when temperature increases, what will happen? Three transistors based on experiment. Okay. So when temperature increases, when temperature increases, three transistor parameters are changed. Who are they? Anyone? Temperature increase ஆகிறப்போ டிரான்சிஸ்டர்ல 3 parameter சேஞ்ச் ஆகும். இவங்க தான் நமக்கு தலைவலி கொடுக்குறவங்க. யார் அவங்க? ஃபர்ஸ்ட் ஒன் யாரு?
Reverse saturation collector current, sir.
So the first one is ICO. It is called reverse, okay, collector saturation current. Yeah, very good. Next one.
Built-in voltage, sir.
VBE, built in voltage. Third one.
Forward
Beta
current gains.
forward current gain. Okay, so we will discuss one by one, and we committed with the ICO, right? Reverse saturation current. So anyhow, I want to repeat this. First one, ICO. Okay, so what we discussed, when temperature increases, what will happen? When temperature increases, ICO decreases.
Increases,
ICO
sir.
increases. So how much?
Increases, sir.
How much, ma? How much?
7%, sir.
For every 10-degree rise in temperature, right? It's very important. For every 10-degree rise in temperature, ICO becomes double. Okay. For every 1 degree rise in temperature, ICO increases by 7%. That we know, right? Okay. Now, what will happen if ICO increases? What is the impact, okay, of increasing ICO? So when ICO increases, what will happen? Anyone? The equation is very important. Okay. So we know IC, which is equal to actually beta times IB plus, we want to consider this minority current also. Here it is beta. So here it is 1 plus beta. This equation, how it came, okay, that yesterday we derived it, right? So now, so what is the conclusion? When ICO increases, right? I will take some other color. Yeah. ICO increases what will happen to this IC? IC increases. If IC increases, then what will happen to the Q point? Then Q point will be shifted. Okay, that we will discuss. Now coming to today's class. Okay, put the heading cutting voltage VB. Yes, are you with me? So this was yesterday class now. Now this is the new topic. So now when temperature increases, what will happen actually? What will happen to this cutting voltage? Any idea? When temperature increases, yeah, VBE decreases. Okay. So how much? Any idea? For every 1 degree rise in temperature, T stands for temperature. Okay. VBE decreases by 2.5 millivolt. Okay. So please make a note based on experiment. For every 1 degree rise in temperature, when temperature increases by 1 degree, okay, the VBE decreases by 2.5 millivolt. Okay. Suppose I want to write in terms of equation, so change in VBE with respect to temperature, which is equal to 2.5 millivolt per degree Celsius. Per degree Celsius. Okay. The unit for volt is millivolt, temperature per degree Celsius. Actually, it is decreases, so you want to put minus. Okay. So this equation is very important. Please make a note. The change in VBE with respect to time, sorry, with respect to temperature, which is equal to minus 2.5 millivolt per degree Celsius. Okay. Yeah. If cutting voltage decreases, how it impacts IC? Or what will happen to IC? Any idea?
Sir, increases.
Increases. How? Can you justify how?
Sir, reverse saturation current increases, so IC increases, sir.
Based on cutting voltage, I am asking. Now my question is, if cutting voltage increases, then what will happen to IC? Obviously, IC increases. How? Cutting voltage decreases, right? Yeah. Cutting voltage decreases, then how IC increases? That's my question. From my previous class, okay.
Sir, IB increases, sir.
How IB increases?
The IB is equal to VCC minus VBE by RB.
Yeah, thank you. So from my previous class, okay, take my first problem, okay, on DC load line. I have taken on a common emitter amplifier. And on the input loop, and we have derived this equation for IB by applying, what is this? KVL at input loop. I equal to V by R. So IB equal to, this is by RB. So this is my applied voltage VCC minus VB. The equation now, orga. IB, which is equal to VCC minus VBE divided by RB. Okay, let me take this equation from my previous class. Yeah, this one. Can you see this? To calculate IB, we applied KVL at the input loop and we derived this, right? Yeah, by applying KVL at this input loop, okay, we derived IB equal to VCC minus VBE divided by RB. Now take that. Yeah. So now, if VBE decreases, what will happen? Yeah, VBE decreases when temperature increases. If VBE decreases, what will happen to IB? IB decrease or increase? Anyone? VBE, actually this is subtraction, right? So VBE decreases, IB increases. Okay. If IB increases, yeah, if IB increases, what will happen to IC? IC, we know beta times IB plus 1 plus beta times ICO Okay, actually what is happening here? IB increases, yeah, IB increases, IB increases, then what will happen to IC? IC also increases, right? So what is happening? When temperature increases, okay, VBE decreases. If VBE decreases, IB increases. IB increases, then IC also increases. Okay, this is the flow. Please make a note. Okay. So when temperature increases, actually VBE decreases. If VBE decreases, IB increases. If IB increases, IC also increases by using this formula. Any doubt? Shall I move? My final parameter is what is that? Forward current gain. The third one, forward current gain beta. Okay. Now, when temperature increases, beta increase aguma, decrease aguma. Any guess at least? Just a guess. When temperature increases, beta also increases. How much? Okay. Here, this is the beauty. Why silicon? Why not germanium? Here, I will give the explanation. For silicon transistor, okay, beta. Any guess? Silicon transistor la what will happen? Germanium la enna nadakum appadinu. Yeah, I will write. For every 100-degree rise in temperature, beta becomes double. Beta becomes double for silicon transistor. For germanium, okay, for every 50-degree rise in temperature, beta becomes double for germanium. Not my point. Now my first question. Beta என்னது current gain. Current gain increase ஆச்சுன்னா is it an advantage or disadvantage? Anyone? If beta increases, is it an advantage or disadvantage? Ma current gain increase ஆகுதுன்னா advantage தானே இல்லையா? Guys, are you with me? Voluntary யாருமா 2 பேர் எடுத்தோமாமா? Yeah, thank you. Ma beta increase ஆகுதுன்னா current gain வந்து increase ஆகுது. Current gain increases அப்படின்னா is it an advantage or disadvantage? Any guess at least?
Not advantage, sir.
Why? Ma
Sir,
current gain அதிகமாகுதுன்னா advantage தானே. I want to generate more current. If current when temperature increases, if current gain increases, no, then automatically I will get more current from transistor. Then why it is a drawback?
Sir, IC வந்து அதிகமா increase ஆயிருவாங்க sir.
IC increase என்ன ஆயிட்டு போகுது என்னப்பா?
Thermal runaway ஆகும் sir.
Thermal runaway.
Thermal runaway ஆகும்.
Thermal runaway ஆகுமா? You studied thermal runaway and all. Yeah? Who is that? You know thermal runaway from your EDA.
Yes, sir.
What is thermal runaway?
Sir, it, output current increases enormously. That is thermal runaway, which will affect the transistors.
Yeah, how
Sir,
it is affecting the transistor?
breakdown ஆயிரும் sir. Temperature ரொம்ப increase ஆச்சுன்னா breakdown ஆயிரும்.
Okay, that is ED point of view. Okay, then circuit point of view I will explain. what is thermal runaway. It is important 2 mark, okay, in unit 1. Okay, my next topic after discussing biasing voltage, after discussing all the biasing techniques, then we will discuss what is thermal runaway. It's very important 2 mark. At the time I will explain what is thermal runaway circuit point of view. Okay. So obviously beta changes, that is a drawback, right? That is not a an advantage. It is a disadvantage, right? Why? Because when beta changes, what will happen to this IC? IC equal to, we know, beta times IB plus 1 plus beta times ICO, right? Yeah. If beta increases, then what will happen to IC? If IC increases, what will happen? Q point will be shifted. That's the expected answer. Okay. அதனால தான் கேட்டேன் ஐசி இன்க்ரீஸ் ஆச்சுன்னா என்ன அப்படின்னு. ஐசி இன்க்ரீஸ் ஆகுது, அது டிக்ரீஸ் ஆகுது, ஏதோ ஒன்று ஆச்சுன்னா ஆட்டோமேட்டிக்கலா என்ன ஆகும்? கியூ பாயிண்ட் நம்ம எங்க ஃபிக்ஸ் பண்ணிருக்கோம், அது சென்டர் ஆஃப் தி டிசி ஒன்று ஃபிக்ஸ் பண்ணியிருக்கேன். இப்போ எனக்கு ஐசி ஆஃப்டர் சம் டைம் பிகாஸ் ஆஃப் த கான்ஸ்டன்ட் டிசி வோல்டேஜ் அண்ட் டெம்பரேச்சர் இன்க்ரீசஸ், 3 பேராமீட்டர் சேஞ்ச் ஆகிறாங்க. அந்த 3 பேர் இப்போ என்னதான் பண்றாங்க? ஆப்வியஸ்லி ஐசியை சேஞ்ச் பண்றாங்க, ஐசியை இன்க்ரீஸ் பண்றாங்க. அப்ப when IC increase, what will happen? The Q point will be shifted. If Q point will be shifted, what will happen? You never get undistorted output. Okay, you will get distorted output. Then you never get stable output. Then you will get unstable output. That's the conclusion. Okay. Now here, coming here, why silicon? Why not germanium? See this. For every 100-degree rise in temperature, but for germanium, for 50. So what's the meaning? Who can withstand high temperature? Silicon or germanium? Silicon la 100 degree silicon அப்ப எது வரைக்கும் டெம்பரேச்சரை தாங்கும்? It's the meaning of withstand, right? It can tolerate or it can withstand up to 100 degrees Celsius. See the beauty? 100 degrees Celsius வரைக்குமே பீட்டா எதுல கான்ஸ்டன்டா இருக்கும்? சிலிக்கான்ல கான்ஸ்டன்டா இருக்கும். பட் வேறஸ் ஜெர்மானியம் 50 டிகிரி ரைஸ் ஆச்சுனாலே ஆட்டோமேட்டிக்கா ஜெர்மன்ல என்ன ஆகும்? பீட்டா becomes double, and what will happen? Q point automatically will be moved. Then you will get distorted output. Okay, so this is called thermal stability. Make a note. Thermal stability. What do you mean by thermal stability? The stability against temperature. Thermal means temperature, ma. Okay. So stability against temperature. Who can withstand more temperature? Obviously silicon, because for every 100 degree rise in temperature, the beta becomes double. So this is the expected answer. Okay, why silicon? Why not germanium? The answer is actually thermal stability, but you want to know what is thermal stability. Okay, what is thermal stability? Stability against temperature. How? For silicon transistor, for every 100 degree rise in temperature, beta becomes double. Whereas for germanium, even for 50 degree rise in temperature, it becomes double, right? 100 degrees Celsius, please make a note. Okay, so now got the idea?
Yes, sir.
So now coming to the interesting part. Okay, so what we are doing, I am increasing or I am giving constant voltage, okay, to the junction. So after some time, what will happen? Temperature increases, or actually you are giving, okay, or you are increasing the biasing voltage. In some way also you can assume. So when you are increasing the biasing voltage, what will happen? Temperature increases. Now when temperature increases, what will happen? 3 transistor parameters are changing. Who are they? ICO, VBE, and beta. Okay, so ICO increase or decrease? ICO increases, VBE decreases, beta increases. Okay, because of these 3 things, what will happen to IC? IC always increases. If IC increases, then what will happen? Q point will be shifted. If Q point will be shifted, then what will happen? We will get distorted output. Okay, So now make this a flow chart. First constant voltage, and we are increasing the voltage, temperature increases. When temperature increases, three transistor parameters are changing. Okay, because of these three parameters, IC increases. Okay, if IC increases, what will happen? Q point will be shifted, so you will get distorted output. So how to stabilize the Q point? Actually, we want to fix the Q point irrespective of ICO, VB, and beta. So how to stabilize the Q point? Have you taken this flow chart? It's very important. ஒரு flow chart கொண்டு வந்திருக்கேன் அவ்வளவுதான். So when temperature increases, ICO, VBE, and beta increases. So because of these three changes in the transistor parameter, obviously IC increases. That you know how IC increases, right? Now my question, if IC increases, obviously Q point will be shifted. So how to stabilize Q point irrespective of the changes in ICO, VBE, and beta. So how to stabilize? Stabilize பண்றதுக்கு தான் we are having stabilization techniques. Stabilization techniques. We are having two type of techniques. One is called biasing technique, and another one is called compensation techniques. Okay, in biasing, as we discussed earlier, very first biasing. What is the first biasing? Fixed bias. Otherwise, this is called base bias. Next one, collector to base bias. Third one, emitter bias. And fourth one, it's a universal one we are following, voltage divider biasing. In compensation, as I told you earlier, we are having three types of compensation. One with the help of diode, another one with the help of thermistor, and third with the help of transistor. Okay, so diode compensation, thermistor compensation, and the transistor compensation. Okay, so we will discuss one by one. Okay, so before begin with a fixed bias or biasing technique, okay, we want to know the stability factor. So it's very important. Put the heading stability factor. Okay, so got the flow. Temperature increase ஆகிறப்ப நம்ம ஆட்டோமேட்டிக்கா என்னது Q point shift ஆயிருது. இப்போ எனக்கு Q point how to fix the Q point, okay, or how to get a stable Q point. For that we are having stabilization techniques. Okay, in order to explain this stabilization techniques, you want to know stability factor. Okay, so what is stability factor? That I will explain. Okay, actually we are having three type of stability factor. Stability factor S, stability factor S dash, and the stability factor S double dash. Okay, in my previous class I told, okay, don't change the order. First ICO, then VBE, then beta. Always don't change the order. Now you can understand why I told that. Okay, so now stability factor S. Stability factor S. What is S? S equal to The rate of change of, actually what is changing here? IC. IC changes with respect to ICO, with respect to VBE, with respect to beta. If it is with respect to ICO, it is the stability factor yes. With respect to VBE, stability factor yes does. With respect to beta, stability factor yes does. In all cases, who is changing? IC. So the change in IC with respect to collector, reverse collector saturation current at that time at constant, overall constant, remaining area, constant VBE and beta. So you want to treat VB and beta as constant. Okay. So this is the definition for stability factor yes. Okay. Let me define here. Rate of rate of change of IC with respect to ICO at constant VBE and beta is called stability factor yes. Okay. So got it. Guys, are you with me?
Yes, sir. Yes, sir. Yes, sir. Yes.
So what is stability factor yes dash? Anyone? Any idea? Can you define stability factor yes dash? Anyone? What is yes dash? Again the change in collector current, but this time with respect to what? Guys, please.
VBE, sir.
Yeah, thank you, ma. So VBE at constant. இப்போ யாரெல்லாம் கான்ஸ்டன்டா இருப்பா? ICO and beta. Now can you write the definition by yourself? Rate of change of IC, this time with respect to, instead of ICO, replace this one by VBE at constant ICO and beta is called stability factor S dash. Please write the definition by yourself. Vipin, are you there?
Sir, yes, sir.
What is stability factor? Yes, double dash.
Sir, rate of change of IC with respect to beta, sir.
With respect to beta at
At
constant.
constant VBE and IC naught.
Thank you. So now got the idea. Yeah, order change பண்ணக்கூடாது அப்படின்னு. Because to get S, S dash and S double dash. Okay. அதனால சொன்னேன். So always please follow the order. First reverse collector saturation current ICO, then cut in voltage VBE, and finally beta. So ICO, VBE and beta. Okay. So any doubt till now?
No, sir.
So you know what is stability factor? Okay. Yes, yes. Actually, in general, what is stability factor? The rate of change of collector current. With respect to, it may be VBE or it may be ICO or it may be, what's the final guy? VBE, ICO and beta, right? If it is with respect to ICO, that is called S. With respect to VBE, that is called S dash. With respect to beta, that is called S double dash. Okay. So now got the idea. It's very simple, right? Today's my aim. I want to derive the stability factor. Yes, it is sufficient. No need to derive S dash and S double dash. So general expression for yes. Shall I move? Have you taken this? Guys,
Yes, sir.
Yes, sir.
so put the heading general expression for stability factor S. It's very simple. It's a 2 mark. Okay. Most probably my first 2 mark. Okay. In the last 2 years. Derive the general expression for stability factor S. If you will derive the general expression for stability factor S, you will get S equal to 1 plus beta divided by 1 minus beta times, right? 1 plus beta divided by 1 minus beta times change in IB with respect to IC. It's very important formula. Please make a note. This one actually we are going to derive. But before derive this, I want to give the final expression. If you will derive S, then you will get S equal to 1 plus beta divided by 1 minus beta times change in IB with respect to IC. Have you taken? Now, shall we derive? Please listen, okay? We know that நமக்கு தெரிஞ்சது ஒரே ஒருத்தர் தான் யாரு IC equal to beta times IB plus 1 plus beta times ICO. Okay. What is S? Anyone? What is S? Change in IC with respect to ICO. Okay. So now differentiate. Take equation number 1. Differentiate equation number 1 with respect to IC. I will let you know why. So now what will happen? Now differentiate the above equation with respect to IC. So what is the differentiation of IC with respect to IC? Anyone? Differentiation of IC with respect to IC. Differentiation of IC with respect to IC. Okay, which is equal to here beta is constant. So what will happen to IB? So differentiation of IB with respect to IC. Okay, plus this is 1 plus beta is a constant. So what will happen to ICO? Differentiation of ICO with respect to IC. Any doubt? Guys,
No,
shall I
sir.
move? So now what
Yes,
is
sir.
this? It is 1 which is equal to beta times change in IB with respect to IC plus 1 plus beta times change in ICO with respect to IC. Okay. Actually what I am looking? I am looking for this equation S equal to change in IC with respect to change in ICO. So now bring this beta to the left hand side. So it becomes 1 minus beta times change in IB with respect to IC, which is equal to 1 plus beta times change in ICO with respect to IC, right? So now bring this 1 plus beta to the left hand side. So it becomes 1 minus beta times change in IB with respect to IC divided by 1 minus beta, which is equal to change in ICO divided by change in IC. But what is S? Change in IC with respect to, therefore S which is equal to change in IC with respect to change in ICO, right? So now take the reciprocal. So you will end up with 1 plus beta divided by 1 minus beta times change in base current with respect to collector current. So this is the final expression. So very simple derivation, okay, to get the general expression for stability factor. Please note on this. புரிஞ்சா derivation? It's important 2 mark. Derive the general expression for stability factor S. Have you taken? You know the fundamental equation, okay? This equation you know, okay? Simply what I did, differentiation of the above equation with respect to IC. Then after that simple manipulation, then you will end up with this one, right? So please. So any doubt till now? Guys?
No, sir.
No, sir.
Right. No doubt. So let's start the biasing technique or is it enough for today's class? Yes, I want to start the next topic, but the time is it's already 4. Okay, 2 more minutes. So I think so today we will wind up here, okay, and we will start the new topic by next week. Most probably the biasing technique by Tuesday. Is it okay or shall I continue? Speak something. Is it okay? Or shall I start the next topic? Is it enough or shall I start the next topic? So thank you for your attention. Thank you.
I think that